Okay, so in the last class we had started to discuss about something known as hidden Markov model. So before coming to hidden Markov model, we had basically discussed something known as basically we had discussed probabilistic models. So what are these probabilistic models? Probabilistic models basically, or rather the probabilistic transition state transition models. So to explain the concept of probabilistic transition models, so we had considered this problem of the labor market status, right? So we had we are studying the labor market dynamics, and we were basically considering that every person, every single person who is part of the labor market, they have three states. One is employed, the other is unemployed, and the third is O, that is out of the labor market. That is for whatever reasons they have made themselves unavailable to work further. Okay, so basically what we had is like the data which we are considering is the basically we consider two types of data. One is the macro level data, the other is the micro level data. What is macro level data? Macro level data is basically like at every given time point, let's say every quarter of the year, total how many people in the labor force are employed and how many are unemployed. That is to say, number of employed people as a function of time t and number of unemployed people as a function of time t. These two things, these two numbers taken together as a vector, this for this was these were the observations, or these were the variables in case of the macro level models, which is directly modeling the labor market dynamics. But this thing which we had tried to express in term of a micro level model. What was the micro level model about? The micro level model was about an individual person for whom we are trying to basically model the state. The basically they are the state of their employment, or as they call it, the labor market attachment. State of labor market attachment. And as we saw earlier, this labor market attachment state can take three possible values: employed, unemployed, and out of the force. Okay. So now and we also, so basically what we were doing is that we were considering the transition probabilities. And that is to say, we considered a transition matrix like this effectively. So basically we had these states E, U, O, U, O, and E, U. Let's say that if someone goes out of the labor market, they will not come back. Or maybe, or let us also consider the possibility that they may come back. Let's consider that also. So what are we saying basically? So here we are basically, what we are doing here is that we are basically computing some probabilities. So what are what are these? So these we call as PEE. This we call as PEU. This is PEO. Similarly, this is PUU. This is POU, etc., etc. So what is PEE? PEE is nothing but the probability that of what? The probability that ST is equal to E, given that ST minus 1 is also equal to E. So what does this mean? This means the probability that given the person was employed at time t minus 1, what is the probability that in time t also they will continue to remain employed? Okay. Similarly, PEU means the probability that ST is equal to U, given S t minus 1 is equal to E. That means what? That means what is the probability that given the particular person was employed in time t minus 1, what's the probability that they will lose their job in time t and so on. Okay, so basically these kinds of probability values we calculated, and then we are trying to like import these probability values to study or to model the macro level dynamics, right? We expressed like we actually discussed in detail how these numbers or how the dynamics of these numbers can actually be expressed in terms of these probabilities, right? I hope you remember that. Now we said that these state variables ST, which basically denotes the labor market attachment of every person or of any particular person, like we here what we are doing is that we are defining our dynamics on the on that state variable itself. But then we decided that this is not a great idea. Why? Does anyone or that is we decided that defining this kind of a dynamics on this state variable itself is actually we are it's making a simplifying assumption which misses out various details. So does anyone remember why we decided this is a simplifying idea and this is too simple or simplistic?
Sir, because it doesn't consider all the sectors of employment. For example, it doesn't like, for example, there's some jobs for software engineers, and someone is, let's say, he's a doctor or some other profession. So it doesn't consider all the professions.
Right, right. So basically the state. So basically here the employment status of a person at any given time is considered to be just a function of their employment status in the previous time point, nothing else. But this way, but that's not a very good assumption, because this is basically missing out on several other factors which are that is even if I was employed earlier, that need not mean that I am going to be employed now for like equally for different people. For some people the probability of retaining their jobs may be high. For some other people the probability of retaining their jobs may be low. Now what are the factors which decide these probabilities? A lot of things may decide, like for example which sectors like as you said which like this particular person may be working in a particular sector, but it may happen that that sector is undergoing a recession at this particular point of time, or it may happen that this particular person like they have certain health related issues due to which it's difficult for them to retain the job, or maybe something to do with their qualifications, etc. And there can be so many other factors also. So basically we cannot explain the behaviors or of every individual with a single model like this. So what is the remedy sought, or at least in the paper which we were seeing yesterday, that is a study by the International Monetary Fund. The solution there is basically you define a hidden state variable, say Z. Okay. This like at time t1 z1 takes a particular, the hidden variable z1 takes a particular value. Then at time 2 the hidden variable takes another value z2, all the way says at any point t it takes a value zt minus 1, then zt, then zt plus 1, etc, etc. Okay, so these are basically the hidden state variables. Why are they hidden? Because they are not directly measurable. We cannot directly measure, just like we cannot directly measure all the factors which may be influencing the any particular person's workforce attachment. So like we just assume that there are a bunch of factors which are all somehow encoded by these variables. Okay, so these are like you can consider these as encoding variables. Okay. Now, in case of a discrete, in case of a hidden Markov model, the assumption is that these variables, they are discrete. Okay. Assumption number one, the ZT are discrete. That means what? That means there is a particular set. Let's denote that particular set by, say, this curly Z. And let's say this like these state values, let's call them as, say, small z1, small z2, up to small z capital K. Okay. So these are the set of hidden state values. So what these, so as I said, the hidden variable basically represents some like all the various factors which influence the person's labor market status, but we are not specifying what those factors are. We are just in like saying that those factors are somehow encoded by these variable. Now these variable, it consists of k possible values. Now what is the value of k? Is it 10 or is it 100 or is it 1000 or what? So that is, again, now this k, this is basically a designer's choice, that is, or a modeler's choice. So there is no clear-cut answer to this question how you should choose k. But if you are a modeler, then you may, like, you will find your own reason for choosing a value of k. But depending on the situation, or if you can't choose k, then also fine. You can actually try out different values of k and see which which value fits the data the best. Now, so what does this K, capital K, mean? So it means that there are capital K possible conditions, or capital K possible types of situations which may affect a particular person's employment status. Okay. Now, the particular, so as again to remind, these Zs, they are hidden, they are not measurable. I cannot measure them. That's why I call this model as a hidden Markov model. Okay. Now, but what can be measurable is is basically the person's labor market adjustment. So the thing which we are calling as S earlier, so let's call that as X. Okay, or maybe, sorry, not X. Let me call it as Y. Okay? Y1, Y2, YT minus 1, YT, etc., etc. So these Y values, these are observable. I can observe this. Now what is happening? Now the model comes in. The model has the following assumptions, that there is a distribution like this. From Z1 to Z2, there is a probabilistic distribution. Similarly, from Z1 to Y1, there is a distribution. From Z2 to Y2, there is a distribution, etc., etc. So there are basically two family. So like, as you can see, what is happening here is that, so in this case, in this model, it was this S variable whose values was changing from across time with respect to a probability distribution. In this case, it's really the values of the Z variable which are changing across time according to a probability distribution. And the observation at every given point is basically dictated by the hidden variable at that particular time point. So what the model is saying is something like this. Like we have like the model, so the model's assumption is there are probability distributions like this, that given zt equal to, that is given zt minus 1 is equal to I, what is the probability that zt equal to j, and that probability is expressed as a of ij. Now what does this mean? This means that given if we know, given that the hidden variable or hidden state variable took the ith value at t minus 1 time, what is the probability that it will take the jth value at the tth time? What is the ith value and what is the jth value of the hidden variable? So as we have already said, the hidden variable can take, say, k different values. So I can be any number from 1 to k, and j also can be any number from I to k. So what the, sorry, 1 to k. So what these states are, or what the ith state or jth state actually indicate, that's not of much use to me, because like you can say that these are you can say this is basically some kind of a proxy. That is, I am not really interested in interpreting this z variable. But there is a matrix A which I call as the transition matrix, and Aij is basically the giving you the probability that if the model is in state I at time t or t minus 1, what's the probability that at time t it will be in state j. Okay? So that is what is indicated by this transition distribution. So this kind of, this is basically the same as this particular matrix. Okay, but the only difference is that here that there was only the observable parameter which we are calling as s. Now they are like that is the state variable was, it's we are considering the state variable and the observed variable as the same thing, and which we called as s, and we are denoting a probability distribution over it. Now we are considering them separately. That is, there is a state variable which we cannot observe, there is an observable variable which we are observing, and the dynamics happens at the level of the state, not at the level of the observable. Okay? But the observable depends on the state. So that is, that dependence is according to this kind of a distribution which we call as emission distribution. So that distribution is something which we call as f. What is this f? It tells us that given at any given point t, if the hidden state is x, then what is the probability that the corresponding observation is going to be y. So so that is, that probability is encoded by this fxy. Now, what kind of a distribution this fxy is, that depends on so many other things. It depends on what kind of variables these y's are. Note that I have already said that this z, this is a discrete variable, and it takes capital K number of values, namely 1, 2, 3, 4 all the way up to capital K. Okay, but I have not said anything about y. This can be discrete, this can be continuous, it can be anything. So so depending on what kind of a variable y is, similarly we'll have to choose a probability distribution f. Okay. So like we know that not all probability distributions work on all kinds of random variables. Say for discrete variables we have, say, categorical distributions or Poisson distributions, etc. For continuous variables we have Gaussian distribution, gamma distribution, etc. So depending on what kind of variable y is, we have to choose f. And finally we have the what is known as the initial state distribution. That is, what is the probability that the hidden variable at the first time point at t equal to 1, what value it chose or what value it took. Okay, so that is called the initial state distribution. At any given point, this z can take capital K different values. Similarly, at t equal to 1 also, this z can take any of those capital K possible values. That distribution only for the first state, irrespective of the observations, is estimated, like is encoded by this thing. So the model, now this hidden Markov model, it has three parameters. One is the initial state distribution, another is the transition distribution, the other is the emission distribution. Okay. Now what do we do with this kind of a model? We can do several things. One is that estimate z given a sequence of observations y and the parameters pi, a, and f. That is, if you have these, so as I said, these what we are calling as y, these are observable, but the z's are not observable. We cannot observe them directly. So what we are saying is that you can estimate the z. That is, you can, like, even if you cannot observe what these things stand for, what the hidden variables stand for, you can try to estimate, say z1, whether z1 is equal to 1 or 5, or whether z2 is equal to, should be equal to 3 or 4, or whatever values each z can take at each of the time points. To estimate that, you need the sequence of observations as well as the model parameters. Okay? So this is one class of problems for which there are specialized algorithms. We will not study those algorithms in this class, but this is just for you to know. The second thing is, the second class of problems is given a set of sequences like this, suppose you have like one sequence of y which consists of say 100 observations, then you have another sequence of y that also has 100 observations. This way you have several sequences of y, a set of sequences of y. Now given that, you have to estimate the model parameters. That is, you only have the time series of say for the, you have that the employment status of say 100 or 1000 different people for 100 consecutive months. Okay, and now you have only that data. So that is, you have one sequence of EU, 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 O, EO, O, EU, EU, like one sequence there is. Then for that is for like laborer 1. For laborer 2, you have another sequence like this. For laborer 3 also you have a third sequence like this. So you basically have lots of sequences of the observable variable y and nothing else. Now using these sequences, you have to try and estimate all the model parameters pi, a and f. That is your second class of problem. Again, how we do that is beyond the discussion in this class. Let us just assume that there is an algorithm to do that, and that algorithm we call as the Baum-Welch algorithm. So what is the algorithm? It is called Baum-Welch algorithm to estimate HMM model parameters. Now suppose you do these things. Suppose you are able to estimate the model parameters, or you are able to estimate the hidden states. Then what will you do with it? Why is it important? So one thing that you can do is forecast the future values of y given a sequence and the model parameters. So suppose like you have seen the particular, like suppose you know the model parameters, or you have estimated them, and you have seen a particular person's employment status for say 50 months, and then you want to predict it for the next 50 months. Now if you have learned the model parameters well, and you have got the initial sequence, then it will be possible for you to make a forecast of the values of y for the next 50 time series. Now, it will not be like a confident forecast, because as you know, this is a probabilistic model. From any given state, even if I am currently at state number 1, from at the next state, this model tells me that from state 1 I can go to state 2 with 0.6 probability, or state 3 with say 0.4 probability. But it does not tell me that exactly which state I will go. That's a strength of the model, because it's like it's capturing the uncertainty of the system. So if I want to forecast the future values, I will not be able to make a confident forecast. I will have to, whatever forecast I am making, I will have to quantify it with the notion of probability. I can say that if this has been the like the employment status for the past 50 months, then it's next month probably this person is going to be employed with a probability 0.6, but there is also a 0.35 probability that she will remain unemployed, while there is even a 0.05% or I mean 5% chance that she will be out of the labor market. Okay, so these kinds of statements I will be able, these kinds of forecasting I will be able to make if I have the sequence and the model parameters. Another thing which I can do is sequence classification. What is sequence classification? So like this, in our lecture number 2 of second module, we had discussed several time series related problems. So sequence classification is like, suppose you have different time series from different like let's say the labor market time series for different people. Now based on those time series, by looking at those time series, you are trying to classify whether which sector this particular person belongs to. Okay, say for that is you for the employee 1 or for candidate 1, you have a 100-month long labor or employment status, and then for employee number 2, again you have a 100-month long employment status, etc., etc. And you also know that like employee number 1, let's say, belongs to the software sector, employment number 2 belongs to the retail sector, Then employee number 3, let us say you again you have their employment status for say some 100 months, and you know that they belong to the manufacturing sector, etc., etc. Now with these kind of labeled data like this, so in this case the class labels are the, so basically your input is the time series and your output is the class level, that is whether it is software or manufacturing or whatever it is. And what is the task? The task is given a new person's time series of employment status, you will have to predict whether this person, which sector this person belongs to. So that's a type of a sequence classification person. So how will you do it? That is to say, so you have got examples of time series from different sectors. Say for software sector, you have got let's say 35 observations, so 35 time series. Manufacturing sector, let's say you have got 50 time series. Then some other sector, maybe you have got like maybe 100 time series and so on. So now what you are going to do is, as I said earlier, if you are given a set of sequences, there is an algorithm to estimate the model parameters. So what you do here is that for every class or for every class level, you train a different HMM model. All right. So that is there should be one set of model parameters for class 1, which may be the software. Another set of model parameters for class 2, which may be manufacturing, etc., etc. Okay. Now, so let us say that this way you get like for every sector you get a different model set of different model parameters. Say for you say theta 1 are the model parameters. By theta 1 I mean the pi 1, a1 and f1. This is the parameters for, let us say, software. Then theta 2 is a set of parameters, let us say pi 2, a2, f2. These parameters are, let's say, for manufacturing. Theta 3 is another one, pi 3, a3, f3, etc. Fine. Now what is the task? The task is, given a new sequence y, which is like say y that is from t equal to 1 to, let us say, capital T, which may be some 100 or 150 or whatever. So now based on this, try to classify whether this person belongs to the software time series software, or to the manufacturing, or to this third sector. Let's call this as, say, education sector, education. So this is what you have to classify. So how do you do? You basically try to calculate which of these HMMs, so these are three hidden Markov models, three HMMs. So the basically what you try to see is which of these hidden Markov models is most likely to produce this output y. So basically here you calculate P of y given theta 1. Here you calculate P of y given theta 2. And finally here you calculate P of y given theta 3. Right. So now how do, so suppose I have calculated these three probabilities. Okay. Now what is, how do you classify this? Suppose the answer is that you just like, so this is basically saying how likely this observation sequence is from this HMM, how likely this observation is from the second HMM, how likely this observation is from the third HMM, and so on. So whichever HMM is most likely to have predicted this particular y, you predict that as the class level. So basically, say suppose, so we can say that, let's denote the class level as C. C is equal to argmax over K P of y given theta K. Right? So whichever model gives you the maximum value, or whichever value of K gives you the maximum value of this quantity, you use that as the class level to predict the class level. So this way you can do time series classification using hidden Markov model. Now the question is that how to calculate these probabilities. So to calculate these probabilities, you will have to use this that is not such an easy task, but you have to understand that if you know both y and z, that is both the and as well as the model parameters, then it is actually quite straightforward for you to calculate the probability of the full thing. That is, you know both the observations as well as the hidden values as well as the model parameters. Then you can use this formula so to calculate the probability. So this formula basically is straightforward because the hidden value at any given point, the z, let's say zt, depends only on the z value at t minus 1. So z2 depends only on z1, nothing else. Z3 depends only on Z2 and nothing else. And Z capital T depends only on Z capital T minus 1 and nothing else. Similarly, XT depends only on ZT and nothing else. So X1 given Z1, X2 given Z2 and so on. Okay. And the values of these probabilities that you can get from these parameters. So this one comes from pi, the first one. The second one is basically talking about the transition of Z. You know the values of Z, Z1 as well as the values of Z2. Let's say Z1 is equal to 1, Z2 is equal to 3. In that case, all you need to find is you need to look up into this capital A matrix and calculate capital A of 1, 3. That's all. Similarly, these things also you can calculate from F. Why you can calculate? Because you know both X and Z. If you know these values, then you just plug in the corresponding values to F and you can get it. It is that simple. The problem here is that we do not know Z. We know only Y as well as pi AF, but not Z. So what do? We marginalize. We calculate this thing for a given value of Z and then carry out what is known as marginalization. So there are, like in this case, there are some algorithms, I mean not exactly algorithms, some formula for the marginalization, which I will not go into, but basically the idea is that of y given theta 1 is equal to p of y z given theta 1 summed over z. What is z? Like what do I mean by summed over z? Means summed over all possible values of z. So remember that this is not so easy as to just calculate a sum over z, because this z is not a single thing. It's actually like z is basically a collection of z1, z2 all the way up to z capital T, right? That is where, so and each of these can take capital K different values. So when I am saying all over z, so total how many values can z itself take? Yes.
T times K.
K
times T.
Yes.
What is it? So Z1 can take K values. Z2 can take K values. Z3 can take K values, etc. So basically it's and they are all different. So basically it becomes K into K into K. So basically it's like K to the power T. These many possible values are values this thing Z can take. Okay. So you can understand that this is not such a simple thing. You cannot calculate, like if K and T are high, then you'll have to do a huge amount of calculations. Fortunately, it is not so difficult. Like you can actually do this calculation in a rather straightforward way by making use of certain mathematical properties of hidden Markov models. Those properties are straightforward only, but for the sake of time, we'll not go into it. But let us just say that like we can marginalize over all possible values of z to calculate this thing. Now,
Sir, I have a question.
yeah, please.
Sir, how do we comprehend the distribution of Z in the first place using the Welch equation, Welch algorithm?
So the bomb well, so first of all you have to like formulate this kind of a distribution, that is first of all you have to decide how many values Z can take. So that's a choice you have to take. So suppose you have decided that Z can take 10 different values, then you have to calculate distributions like this, that say probability what is that if at t minus 1 Z took the value of let's say 3, then what is the probability that at zt it will take the value of 5, and so on. And I have to give it a particular name. Let's call it as a of 3, 5. Similarly, for other values also we'll have to that is establish these things. So now how to get those probabilities, how to get so this A is basically the state transition matrix whose entries contain these probabilities of the transitions. Now the question is how to get that matrix. So if you have lots of example time series like this, so either this matrix will be given to you by whoever is giving you the problem, or you will have to you'll be given plenty of time series like this, what is I mean plenty of observations of y. Then based on that you will have to estimate this time series A using the Baum-Welch algorithm. So either it will be given to you, or either the parameters will be given to you, or lots of time series like this will be given to you. In the latter case, you will have to apply the Baum-Welch algorithm to estimate this A. Similarly, you can estimate pi and f also. Now f, what type of distribution it is, whether it's a normal distribution or a categorical distribution, that's up to you. But what are the parameters of that distribution, they will have to follow from the Baum-Welch distribution. Now, I mean Baum-Welch algorithm. Now let us come to another kind of another kind of model for time series data, which is known as recurrent neural networks. So this is also a hidden state model, and but in this case the hidden state values can be continuous. Unlike HMM, where we are saying that the hidden variables are discrete, they take capital K different values, but here we can like these can be continuous also. In fact, they need not be single numbers, they can be they can be vector, they can be matrix, they can be tensor, they can be arbitrarily complex. And while this type of model is not probabilistic, but their transition function can be very complex. That is, so here in this example, I am denoting the hidden state variable as S. Okay, at any given time it is ST, and at the previous time point it was ST minus 1. Now, whether this ST is a real number, or as I said, it's a scalar or a vector or a matrix or tensor, it will depend from one situation, one problem to another. So that is the standard dynamics of this model is defined by this kind of an equation. So let's look at this, examine this equation. So first of all, what is X? X is the input to the model at time t. So I mean, let's say some observation is there. I mean, you are provided with a time series to begin with. So just like in the hidden Markov model, we had a time series. In this case, also we have a time series. So let's say xt is the input value or the time series observed value at time t. Now again, this can be anything. It can be a scalar, it can be a vector, it can be a matrix, whatever. Okay. Now assuming that it's a matrix, I mean everything like everything is a special case of a matrix only. So assuming this is a matrix, let's say that there is also another matrix called U, with which we multiply the input to get another matrix. Then there is at any given point there are two things. One is the observed value at that time point, and the other thing is the stored or the state variable from the previous time point. So these two things combined to produce the state variable or the hidden state variable for that particular time point according to this thing. So W and U are basically matrices of the suitable dimensionality. By suitable dimensionality, I mean that it depends on what is X and what is S. So X is of course like the space, the particular type of input we are or particular type of time series that we are considering. Now about S, what kind of variable S is, that is again up to you, up to the network designer, whether you want to consider it as a like a scalar or a vector or a matrix, whatever it is. But whatever it is, whatever you have chosen, you have to choose an appropriate W such that this multiplication makes sense. If it is a scalar multiplication, if this is scalar, then W has like W. Okay, yeah, I mean the scale, matrix can be multiplied by a scalar also. If it is vector, but if it is vector, then you have to make sure that W and this vector are of compatible dimensionalities. Like if this is say 5 cross 1, then W better have 5 columns, otherwise we won't be able to do matrix multiplication, etc. So, and then finally, once you add these two things up, you will get a matrix. Then what you will have to do, you will have to operate that matrix with a function which we called f, some kind of a nonlinear function, using which you will get the state variable for the next step, which is t. Okay, so you had s t minus 1 at from the previous state, and you get xt, the current observation. Like using these two, you calculate what is the current value of the state variable st, and you can, if you want, this is not necessary, you can also have an output at this time point which is some function of the state variable. So again there is another matrix V which you operate upon the current value of the state variable. You pass it through another nonlinear function G to get the output. Again, this whether this is a vector or a scalar or a matrix or whatever is depends on these V, G, etc. And these are all for the network designer to come up to decide. So this is the recurrent neural network. The like it has similarities and differences with hidden Markov model. The difference is that this is not probabilistic. That is to say, given these two things, like what the next state is going to be is deterministic. Like there is no amount of probability involved in the dynamics here, unlike HMM. So the other is that this transition function is quite complex. That is, it does not need to be a linear function. This f can be a non-linear function. This w and u, they can enforce various kinds of transformations on the input as well as on the previous value, etc. So these dynamics can be complex, unlike HMM. One more thing is that unlike HMM, where the hidden state had to be discrete, here it need not be, I mean, not only continuous, but it need not be a single scalar. It can be like, it can be it can be a scalar, it can be a vector, it can be a matrix, even tensor and so on. So there are similarities but or analogies with HMM, but there are crucial differences also. Now, how does our RNN work, recurrent neural network work? So first of all, to do anything with this, first of all, we need all the values of all these parameters, W, V, etc. Note that the time series by which we are considering here, these may be arbitrarily long, but the values of these parameters W, U, etc. or W, U and V, these are the three parameters here. Note that these parameters are not changing over time. That is, the same values of W at t equal to 1 also, you will use these values only. At t equal to 5 also same values, and t equal to 25 also same values, and so on. So the only thing which you need to do is you need to estimate the parameters W and U, and if necessary then V also. Okay. So the X you have, maybe the O also you may have, depending on the situation. Your task is to estimate these unknown values. Now, to do that, you need to just like we have the Baum-Welch algorithm for estimating the parameters of a HMM. Similarly, there are algorithms to estimate the various parameters of the RNN. So, that is called training of the RNN. To train the RNN, you basically have to, you'll have, just like to train HMM, you needed lots of time series. Similarly, here also you need lots of time series to train an RNN. Now, Unlike Baum-Welch algorithm, which is basically based on probabilities, so this is like the algorithms involved to estimate the RNN parameters. They are done by certain numerical optimization methods, which such as gradient descent. So I guess many of you have heard of gradient descent. It's basically a numerical optimization method. It tries to give you there is a loss function which is defined, and it tries to optimize, choose the parameters w, u, v, etc., so that the value of that loss function is minimized. In a sense, it's the same approach as linear or lasso regression, but the only thing is that the parameters are going to be much more complicated in this case. Now, this is this kind of hidden Markov model. So suppose you are able to estimate all its parameters, then what will you do it? So as I said, in case of HMM also, you can use this RNN to predict to forecast the future values of a time series. That is, if you know the observations at any given time point, you can actually try to predict what the outputs are going to be at the subsequent, like at that point, and so on. So you can use it for forecasting purposes, but also for some other purposes, as we'll see. But the thing is that estimation of these parameters becomes difficult if the training sequences are very long. So that is there are some problems known as vanishing gradient problem and exploding gradient problems. So of course, those of you who have done any deep learning course are already aware of these things, but we are not going to the details of these things in this class. Just to get an understanding of it, we are doing basically trying to estimate these parameters through some numerical optimization algorithms, as I already said. So that basically you have to calculate some derivatives, and you will have to multiply those whichever derivative you have calculated, you have to multiply those derivatives with the numbers, like I mean with the values, like at the different time points. Now, if this time series is very long, say t equal to 100 or t equal to 1000 or something like that, you will have to keep on multiplying those gradients like at any given with respect to any given variable time point. You suppose you do the multiplication, then you will have to pass on the gradients to the previous time step. So for that, again you will have to do another round of multiplication here, again to pass on the gradients to here, again another round of multiplication, etc., etc. So you have to do a large number. So basically what you are doing is applying the chain rule of differentiation. Okay, so you may have heard of this algorithm called back propagation, which is used to estimate the parameters of a neural network. So back propagation is an algorithm which is basically based on chain rule. Now, in a case of a recurrent neural network, what we do is basically back propagation through time, BPTT, back propagation through time. That means, like, you calculate a gradient here, then based on that you at time t plus 1, based on that you calculate the gradient at time t, then based on that you calculate the gradient at time t minus 1, and so on. So basically what you are doing is, like, you are calculating like you are doing successive differentiations as if in a chain rule, as you do in a chain rule. And in a chain rule you have to keep on multiplying, so many things you have to multiply. Now, because it's a numerical methods, if you keep on multiplying so many things, then two things can happen. Either the numbers can become very small and tend to 0, or the numbers can become very large and they can tend towards infinity. And whatever thing or whatever software you are using for these calculations, the software will have a certain precision, right? It cannot it cannot represent numbers, let's say, less than 10 to the power minus 100 or more than 10 to the power 100 or something like that. Okay, so if as you go on multiplying and multiplying, it's most likely that those limits are going to be violated. So as a result, your or whatever framework you are using for the computation, it will no longer be able to deal with such small or such large numbers. So either the values which you are, I mean the derivatives which you are calculating, either they will tend towards 0 or they will tend towards infinity. So this will result in some various problems. Okay, so this is the so this is why RNNs are have limited use when that you are dealing with long time series. So to solve this problem, here comes what is known as the long short term memory. So this is also some kind of like basically a kind of neural network. I mean, it's a kind of recurrent neural network only, but here the hidden the hidden variable calculation is much more complicated than the simple RNN. Like in case of RNN, so this is how the hidden variable was calculated according to this simple equation. I mean, there was a single hidden state variable S which was calculated according to this equation. Now here there are many other, like there are two different things. One is the short-term state, or was the short-term memory, which we call as H. Another is the long-term memory, which we also sometimes call as the cell state, that is called C. So conceptually that it remains the same. See, just like in case of RNN, so if you look at the schematic diagram of RNN, so this is what it looks like. Like you have a hidden variable S, which evolves over time. At every time point, there is an input which denoted by X, and it may produce an output which is denoted by O. Okay, so basically the input goes in, interacts with the or rather the hidden state, basically it takes in input, the input, it takes in its value from the previous states. These values interact and produce its new value, the new state value, and also gives out an output. Then the same thing happens in the next time step and so on. The same thing is happening in the RNN also. So if you look at this figure, you will understand. So at any given point, the input is coming in, the stored cell values from the previous state are coming in, these values are interacting, a new cell value is established, a state value is established, and output is given out. Again in the next time point, input comes in, interacts with the updated state value, again updates the state value, gives out an output, and so on. Okay, the difference here is that the state value here, like it's not one, but there are two kinds of state values, the short-term state with a short-term memory H and the long-term memory C. Okay, so how those values are updated at every time point, that depends on this set of equations, or these are sometimes known as the different gates of an LSTM. So and like I will not go into the details of how exactly the sorry, the LSTM works, but you can actually understand it by seeing this figure. It's straightforward only. The thing is that there are a number of these parameters. These UI, WI, UF, WF, UO, WO, UG, WG. So many parameters are there, right? So in case of RNN, we just had one U and one W and one V. There are so many of them. So so basically you have many more parameters in the LSTM, so which is potentially a problem, but it also like if you are able to estimate these the parameter values well, then it gives you a potentially richer representation than RNN, and it does not suffer from the problems of which we mentioned earlier, the vanishing gradient and exploding gradient. Why is it so? That's because of this basically that's the okay. So actually there is a different rationale apart from vanishing and exploding gradient. Also there is another rationale for having the two things. So basically, so like as you can see, in case of RNN, so as you can see, it's the state variable is getting updated at a very various time points. Okay, so that means what? If you are going for a long time series, then the initial values of that state variable, maybe at t equal to 2 or t equal to 5, they will be like completely overwritten by the time we reach say t equal to 50 or something like that. We will not be able to retrieve those because they have been overwritten and changed so many times in between. But this now in certain time series related tasks, it is actually necessary to like store some of the variables or some of the intermediate values, because they may be useful later. This is particularly true in case of say natural language processing related applications, where these RNNs and LSTMs have made excellent progress. That is to say, suppose you have a sentence and you are trying to predict the next word in the sentence. So for that, you do not, to predict the next word of a sentence, you may have to, like, you cannot only depend on the maybe the past one or two words. You may have to look at the early parts of the sentence also. So, right, so that's how that's the necessity of that application. Now, in case of RNN, that is not possible because the old values have long been updated. But in LSTM, you can actually preserve some of the older values unless that is overwritten. So there is that is why this is called long short-term memory. There is a long-term memory as well as a short-term memory. The long-term memory is represented by this variable CT, and the short-term memory is represented by this variable HT, which is updated at every step. HT, just like in case of an RNN, is a normal state variable which gets updated at every step, like according to the equations maintained here. But this long-term memory, this is not always updated. So this is like either its previous value is chosen, or it is updated only if there is a signal to update it. Now, who generates that signal? I mean, the cell only generates that signal based on the input. Only if the cell says forget the previous value, now store the current value, then only it will forget. Otherwise, it will keep passing on the old values. Okay, so that is one way in which the old values of that time series can be preserved with the help of LSTM. Now, so to train an RNN or to train an LSTM, of course, you have to estimate all these parameters, which is a difficult job. But fortunately, we have our toolbox, of numerical optimization algorithms, which helps or allows you to estimate these parameters, provided you have enough data. And what do I mean by enough data? I mean enough time series of these things, and the time series should be long also. There should be many long time series of these kinds of inputs, and if applicable, the corresponding outputs also. Then only we will be able to do a good job of training these models. So these are basically neural network based or deep learning based models, RNN and LSTM, and these models typically require a lot of training data to train them perfectly. Otherwise, they will not be able to estimate the parameters well. Now, these RNN or LSTM, they can be made more complex by stacking one over the other. That is, you need not have an LSTM with a single hidden variable like this. You can, you can have multiple layers of hidden variables just like this. So at any given time, you like the input comes in and you receive the hidden variable or the hidden state value at the first level from the previous time step. You do the calculation, update, and get some intermediate value. Now you go to the next hidden level. Let's say in this case there are three levels of the hidden variables. So you go to the second level of the hidden variable state variables. Again, that intermediate value interacts with the past time in the past time step, whatever the second level had. These values interact. A new value is established, and an intermediate value is passed on to the third level. Again, at the third level, the same thing happens. The third level state variable already had some value in the previous step. Your intermediate representation interacts with that and then establishes a new value of the state variable, and based on that, output is created. So this way, like, you are not there is not a single hidden variable like this, but there is several layers of hidden variables, and the computation of at every layer is passed on to the next layer like this. The same thing can be done in case of LSTM also. the reason is that is having more layers basically gives you greater representative power. As I said, in case of normal LSTM, suppose there is a value which you want to remember for an old value which you want to remember for several time steps before finally removing it. So that can be achieved through an LSTM like this. But suppose you do not want to remember one old value but maybe 3 old values. So in that case, this LSTM will not be enough, because there is only one cell state, so it cannot store more than one state variables. I mean more than one values. So what do you have to do in such a situation? You will have to do these multiple rounds of LSTM, one above the other. So maybe this LSTM, this layer one value will be stored, this layer another value will be stored, third layer another value will be stored, and so on. So this is basically called the stacked representation of either RNN or LSTM, and this enables you to higher representative power. Yeah. And finally, now, in this case also, in both RNN and LSTM, I am not going into the details of exactly how these work or how their parameters are estimated. I will give you a brief idea about what we do with these with these kinds of models. So especially in the domain of time series. So first of all, we can do short-term forecasting. So we have already discussed in case of hidden Markov model. So basically these are what these parameters are giving us. They are basically representing the dynamics of the model, how the state variable changes with with the inputs which we received with the observations. So that is the dynamics of the model. Now, if we know the dynamics of the model, then we can actually predict the output of the model, and maybe we can also predict the like at any given time point t, we can predict the output based on the inputs, and maybe we can also try to predict what the outputs will be at the coming steps. This is known as long-term forecasting. Will happen that sometime the next steps input itself can be predictable. Say for example, say what you are giving out as the output may itself go as become the input for the next step. This kind of situation often arises, that it's not that you are giving inputs separately, but you gave the input once and subsequently at that point you got an output, and that output itself became the input in the next step. So right, so it's like you are generating the time series from its past values. So that's like if you are trying to do that, this RNN can be, or RNNs or LSTMs can be used for long-term forecasting like this. Another problem which we can do using these things is time series classification. Again, as we discussed this particular problem. So suppose you are giving the three different, or like you are given a number of time series. Each time series has a particular level. Like this example which we gave here, the inputs are basically the labor market status of different of different persons, and based on that you have to classify those persons as which sector they belong to. So similar kinds of problems. So this is a classic example of a time series classification problem. Similar time series classification problems are also possible, but the thing is that their inputs of those time series, they can be quite complicated. In this case, of course, the input is very simple. It's like either E, U, or O, right? So it's a discrete variable. But these in general, our time series can have quite complicated input. It can be a vector, it can be a tensor, it can be a matrix, whatever. So all these kinds of complicated input, that is in time series, complicated time series can be classified using this kind of these kinds of models. So basically the way that classification works is as follows. I provide the entire time series as the input. An intermediate representation is formed on the basis of the hidden state, and then based on that intermediate representation, another neural network does the classification problem. So neural network, we know, or most of us know, is quite good for classification. So so this way we can like use the time series classification. And finally, time series translation or mapping. Say use this problem is given one time series, generate another time series. That is map one time series to another one. In case of natural language processing, this is the classic translation problem. Say suppose I give you a sentence in language A, translate that sentence to language B for me. So what is done here is that the sentence in language A is provided to the neural network. The entire time the sentence is provided, the neural network creates an intermediate representation of that. Then it, based on that intermediate representation, there is something called the decoder network, which takes that intermediate representation in, and it generates another time series out of, I mean another sentence or sequence out of it. That is now similar problems can arise in the domain of economics also. So so in such situations, this these kind of time series operations can be used. So I am not going into the any details of how exactly these RNNs, LSTMs, etc. work in these lectures, because simply we do not have time to do that. But what we will do is that later this week, in the either Thursday or Friday, we will see some examples of how to use these kinds of algorithms using Python. That is, our teaching assistants will give a demo in which they will take up some some time series data set and then show how to solve some of those problems, say for related to forecasting or related to classification, using these models HMM, RNN, LSTM, etc., which we studied. Okay, so that brings us to the end of this particular part. Next, I think on Thursday, Professor Pulak Mishra will take one lecture on discrete choice models, and after that, on Friday, the teaching assistants will give the demo on this HMM, RNN, and LSTM, which I mentioned. So, so please join for that class. Okay, thank you.
Hello, sir.
Yes.
Sir, could you suggest some data set to practice these models?
So they will be the data sets will be suggested in the in the demo session on Friday.
Sir,
Yeah.
any could you suggest any data set right in today's class right now?
Okay, so like for example, in the, if you look at your assignment 2 which has been given, so one data set is already provided there as the third choice. So 3 choices have been given to you. The third one is basically a time series forecasting problem. So that is there.